Hello, students. So, it is currently 5 minutes before 8 a.m. on Friday, November 30. I'm recording this because I realize it's not totally clear that I'll cover the amount that I think that I want to cover in class today. So for the sake of this recording that'll be posted for the 6th, which is probably the day you're watching this, I want to just hedge my bets, have some of this done in advance. So, let's start doing some inverse trigonometry. So, here's an important question. Solve sine of x is equal to 1 over 8. All right, that's a straightforward enough question. That's just what inputs result in the sine of 1 over 8. And if you want some motivation, here's some motivation. Suppose you want to build a triangle whose opposite side length is 1. It's a right triangle whose hypotenuse has length 8. What angle should you assign this to be? Well, let's just read off some things we know about it. It's an angle in a triangle, so this angle is between 0 and 90 degrees, or 0 and pi over 2 radians. So maybe I'll say it this way. It's an angle in quadrant 1. I know what its sine is. Its sine should be 1 over 8. I'll just call that angle sine inverse of 1 over 8. And depending on how whatever calculator you like does that, maybe it'll want you to type arc sine of 1 over 8, or possibly a sine of 1 over 8. So, I'll ask you to pause right now and ask your calculator to make this approximation. Figure out whether you have a button that says sine inverse, button that says arc sine, or maybe a sine. If you don't see such a button, then it might be worth pulling up your calculator manual and seeing how to ask it to compute inverse trig functions. As you do that, here's what I'll do. Let's go to our favorite calculators. I'll use the Google calculator. It says that arc sine of 1 over 8 is about 1.2 radians. And notice it wanted this arc sine notation. It didn't like sine inverse. You can also ask it for things in degrees. And if you're using a calculator, you'll literally enter degree mode and compute arc sine. Apparently that's the same as about 7.2 degrees. 1.2 radians? That's not right. I think I lost a decimal place. Yeah, 0.12. That's more like it. All right. So, this stuff up here is the informal definition of inverse sine. Inverse sine of 1 over 8, what does that mean? This means the, in quotes, angle in quadrant 1, or maybe one other quadrant, with sine theta equals 1 over 8. Similarly, you can talk about inverse cosine. What does that mean? It means the, actually with what I've said, the word the is totally appropriate. Angle in quadrant 1 or some other quadrant with cosine theta equals 1 over 8. All right, so, oh, sorry, you couldn't see any of that. Inverse sine of 1 over 8 means the angle in quadrant 1 or some other quadrant. Right? If I asked you for inverse sine of a negative number, that can't be in quadrant 1. You'll have to figure out a different quadrant. With sine equal to 1 over 8. Inverse cosine of negative 1 over 8 means something similar. It's the angle in quadrant 1 or some other quadrant. And notice, if I want cosine to be negative 1 over 8, that's not going to be in quadrant 1. All right, where is cosine negative? It's negative in quadrant 2 or 3. So be one of those two quadrants. So let's try to figure it out. Let's do it graphically. So right, I want to invert the trig functions. I want inverses to the trig functions. Here are sine and cosine. Well, take a look at them. Do they pass the horizontal line test? No. You draw a horizontal line. It might cross the graph of sine or cosine infinitely many times, right? Like you see 4 intersections in this picture. But if you continued this graph on forever in another direction, you'd see infinity many intersections. So are they one-to-one functions? Do they have inverse functions? No. Well, that's a problem. If we want to study inverses to the trig functions, that's bad. I want to study inverses to the trig functions, but the trig functions don't have inverse functions. But you already, know a solution to this kind of problem. It's restriction of domain. And here's, the motivation you already know. There's the squaring function. It's not one-to-one. But if I asked you what undoes squaring, you can still answer the question. The inverse is the square root function. And I put inverse in quotes there because it's not really an inverse. But it's almost an inverse, and how do you get it? Well, you say, well, all of y equals x squared isn't one-to-one, but if I just study that piece of y equals x squared, that is one-to-one. So you use the graph to find, the biggest domain you can on which the function is one-to-one. You invert that. So let's do that with sine and cosine. So here's what I'll do. I'll start at the origin for sine. I'll travel as far as I can to the right until it becomes not one-to-one. So it looks like I can go that far to the right, that far to the left. Aha. So if I restrict that domain, if you only see this bit, sine of x is one-to-one. So you just don't allow everything in the domain. You restrict the domain. And it looks like to get sine of x one-to-one, you need to restrict the domain to, well, let's see, how much of the domain did I use? I went from a turning point to a turning point. That turning point is at negative pi over 2 on until pi over 2. Let's do the same for cosine. In fact, I'll encourage you to pause and just do it for cosine. So we'll start at the origin, and you've already done this, but we'll go to the right as far as we can while still having it be one-to-one. It looks like that's where we need to stop. This much of cosine is one-to-one. So, to get cosine of x to be one-to-one, to get cosine of x one-to-one, you must restrict the domain to 0 to pi. If you go any further, it's not one-to-one. So, let's use that. So, if I only see that much, that's a function that I can take the inverse function to. If I only see that much of cosine, there's a function I can take the inverse function to. That's what we'll mean by the inverse sine and inverse cosine. So, here we've done it. We've restricted the domain of sine of x to negative pi over 2 to pi over 2. The x values here range from negative pi over 2 to pi over 2. We restricted cosine to have domain 0 to pi. Are these things one-to-one? Let's take a look. Let's draw some horizontal lines. Yeah, each of those horizontal lines crosses sine at most once. So it's one-to-one. Same thing with cosine. So are these one-to-one on their indicated domains? Yes. One-to-one functions have inverse functions. So these have inverse functions. here's the definition of sine and inverse. Inverse sine, also called arcsine, is the inverse to sine after you restrict the domain to be negative pi over 2 to pi over 2. So what does that mean? That means if I give you a number y, then inverse sine of y is the angle. Maybe I'll even give that angle a name. Let's call it theta because it's an angle. You should give angles Greek letter names. Not for any good reason, just for conventional reason, and it helps you keep track of what's what. Is the angle which lives in this range, so in between negative pi over 2 and pi over 2, with sine of this angle theta equals y. So inverse sine of y says, I'll tell you the y value, you tell me the angle. Or, yeah, you tell sine the y value, it tells you the angle. Inverse cosine is the inverse function to cosine after you restrict its domain to be 0 to pi. So inverse cosine of y, of an input y, is the angle theta in between 0 and pi, which has cosine of theta equal to this y value. So inverse cosine says, you tell me what value you want cosine to be. So I guess that means like, what x value do you want to accomplish on the unit circle? Inverse cosine tells you the angle that gives you that cosine. Let's read off some domains and codomains. So if you want the domain of inverse sine, well, I guess that means you want the range of sine after you restrict the domain. What's the range of this? And you know how to answer that. It's all the y values you see on the graph. It's negative 1 to 1. So the domain of inverse sine is the range of sine, negative 1 to 1. What's the range of inverse sine? The range of inverse sine is the domain before we took the inverse. Negative pi over 2 to pi over 2. Same thing for cosine. What's the domain of inverse cosine? Well, it'll be the same as the range of cosine. So the domain of inverse cosine is negative 1 to 1. Its range is 0 to pi. Let's also sketch some graphs. So here's the graph of sine after we restrict the domain, the graph of cosine after we restrict the domain. We can get the graph of the inverse function by taking each point and changing its xy coordinates. So because negative pi over 2, negative 1 is on the graph of sine, negative 1, negative pi over 2 is on the graph of inverse sine. The origin, 0, 0 is on the graph of sine, right? Sine of 0 is 0. So 0, 0 should be on the graph of inverse sine. Pi over 2, 1 is on the graph of sine. So 1, pi over 2 should be on the graph of inverse, pi over 2 comma 1 is on the graph of sine, 1 pi over 2 is on the graph of inverse sine. And now, let's just kind of copy things down. I see like a horizontal tangent line there, so I guess this will be basically vertical. So what have I tried to do? I've tried to just copy down the exact same graph, but swap the role of x and y. And now, I'll encourage you to do the same thing for cosine. So what we just graphed is y equals arcsine of x. Let's also graph y equals arc cosine of x here. So, exact same game. 0, 1 becomes the point 1, 0. Pi over 2, 0 becomes 0, pi over 2. Pi negative 1 becomes negative 1 pi. And now we'll just copy down this graph through those points, but we'll try to get like the slopiness of the thing to be correct. Groovy. All right, so there's a graphical approach. Now that we have graphs of inverse sine, you could use those graphs to say lots of things. For example, take a look at that graph. Is it even? Is it odd? Yeah, it's odd, right? It has symmetry over the origin. Inverse cosine, even or odd? Well, you stare at it for a second. You say, oh, wait, it's certainly not even. I can't reflect it over the origin. In fact, here's a thing that's not so hard to convince yourself of. Whenever you take the inverse of anything, the result can't be even. Otherwise, the original function would violate the vertical line test. It's also not odd if you pin down the origin and flip 180 degrees. Oh, you get a different looking function. So it's not even, it's also not odd. It's like odd-ish. It has symmetry over this point. If you pin that point, do a reflection. You can figure out what that means about inverse cosine. We won't do that today. Let's also just use a unit circle to make computations. So let's try to compute inverse sine of 1/2. So what does that mean? That means I want an angle where sine is 1/2. And happily, we've filled out a unit circle. Here it is. And I know how to read off sine. Sine is the y-coordinate. I see a y-coordinate of 1/2 there. See a y-coordinate of 1/2 there. So it looks like pi over 6 and 5 pi over 6 are reasonable choices. So here's not the final answer. Maybe one of those. All right, now let's deal with this condition. This angle has to be between negative pi over 2 and pi over 2. That one's between negative pi over 2 and pi over 2. Like pi over 6 is less than pi over 2. You divide something by 6, you make it smaller than if you divide it by 2. 5 pi over 6 is almost as big as pi. This is not in negative pi over 2 to pi over 2. All right, so inverse sine of 1/2 is equal to pi divided by 6. Cool. All right, so here's one for you to do. So pause the video and do the following. Compute inverse cosine of negative root 3 over 2. So what does that mean? That means I want you to pull out your unit circle, find an angle. It should satisfy that cosine is negative root 3 over 2. That angle must be between 0 and pi. So pause the video, do it. Okay, you did it. Good job. Let's try to do it together now. So since I want cosine to be negative root 3 over 2, that means I want the x-coordinate to be negative root 3 over 2. X-coordinate's negative root 3 over 2. X-coordinate's negative root 3 over 2. So it sure looks like theta equal to, sorry, I should keep this up because I'm still referencing it. Theta equal to 5 pi over 6. Or theta equal to negative 5 pi over 6. Or depending on how you think. Those certainly satisfy this condition. They satisfy that the cosine is equal to negative root 3 over 2. Next, let's think about the fact that it needs to be between 0 and pi. 5 pi over 6 is between 0 and pi. Negative 5 pi over 6 is negative, so it's not between 0 and something positive. 7 pi over 6 is bigger than pi. So those two are not in the right range to be inverse cosine of anything. So the conclusion is cosine inverse of negative root 3 over 2 is 5 pi over 6. And you can just read it off of the unit circle by doing that. All right, so we've talked about right triangle, talked about inverse trig functions in terms of the unit circle, let's also talk about right triangle trigonometry. So let's try to do this. There's an angle alpha. There's an angle beta. This is a right triangle. It's a 4, 5 right triangle. Let's determine trig function in what these angles alpha and beta are. So maybe we'll start with this. Here's one thing I definitely know. Cosine of alpha is 4 over 5. Also, alpha is in quadrant 1. Quadrant 1. It's between 0 and pi over 2. Ooh. So, alpha is a valid number to be inverse cosine of a thing. It's in the right range. Right? The range of inverse cosine is 0 to pi. This is in something smaller than 0 to pi. It's between 0 and pi over 2. So, alpha is equal to cosine inverse of 4 over 5. And that certainly isn't something that we just know how to compute. But now that we can write it down, we can ask a calculator to compute it. If you want to know what approximately is an angle in a triangle, inverse trig functions tell you that. Arc cosine of 4 over 5, if you want radians, is about 6.4 radians. Or about 39 degrees. Neato. So let's notice one thing about this. That's not the only way you could have detected the angle alpha, right? If that's a 4 and that's a 5, then this opposite side, y, should satisfy y squared plus 4 squared equals 5 squared. Gosh, that means y squared equals 25 minus 16 is 9. That side y is 3. So, I also know that the sine of alpha is 3 over 5. Oh, but same thing, this angle is in quadrant 1. It's between 0 and pi over 2. To be a valid number to be inverse sine of a thing, it needs to be between negative pi over 2 and pi over 2, and it is. It's in fact in like only half of this interval. So this angle alpha is sine inverse of 3/5. Give myself space. Let's pull back up that computer. Arc sine of 3/5. And I'm only doing in degrees plus, so I don't have to like backspace as many times. Apparently, that is about, oh, that was 47 degrees. And if I do it in radians, it's about 0.64. My goodness. My goodness. I absolutely should not be trusted to copy down any numbers on my own. So here's the point. Alpha was computed 2 different ways. They better give me the same answer, and indeed they did. So there's some like overlap between what inverse sine and inverse cosine tells you that this is suggesting. Nice. So, pause the video. I want you to do exactly that again. Here's a triangle. There are 2 unknown angles, alpha and beta. Here's a right angle, so an angle of pi over 2. Determine these angles. I'll wait. Good. So, by wait, I mean you'll pause the video and do it. So you've done it now. Let's try to determine these. So I'll do it like 3 different ways. So first let's do this. So to determine alpha, I think I want to know what cosine of alpha is. And cosine of alpha is 4 over c, which is not known right now. So let's determine c. C squared is 4 squared plus 7 squared. Guess we got to evaluate that out. C squared is 16 plus 49 is 9 plus 6 is 15, carry the 1, 65. So it looks like C is equal to the square root of 65. It's not negative because it's a hypotenuse of a triangle, it's going to be positive. All right, so I know what cosine of alpha is. Cosine of alpha is adjacent 4 divided by the square root of 65, which I don't like to see square roots in the denominator. I'll rewrite that as 4 root 65 divided by 65. So now that I have cosine of alpha is equal to a thing, again, this is an angle in our right triangle. It's a valid output to be inverse cosine. So this angle alpha is cosine inverse of 4 square root 65 over 65. Let's write down what that is. Now let's just see if it accepts this. A cosine, for inverse cosine, of 4 times the square root of 65 divided by 65. Yeah, looks like I'm getting about 1.1 radians. Or, if you want to work in degrees, let's see, I guess, well, in degrees is about 60 degrees. I guess I should have known that because 1 is about 1/3 of pi, so this should be about 1/3 of 180. Cool. So you can compute the angle alpha doing this. Oh, notice you can also, I think I'm only going to emphasize the angle. Well, no, I should do both because it says to do both. Let's also compute the angle beta. So it looks like beta, let's see, I know its opposite is while it's adjacent to C. So sine of beta is 4 over 65, root 65. Which again, 4 root 65 over 65. So that means beta is equal to the inverse sine, the arc sine, of 4 root 65 over 65. And let's do the same computation. Let's see what these are about. About 30 degrees, or 0.52 radians. And I guess there's one quick check you can make. Angles in a triangle should add up to 180 degrees or pi radians. The degrees look easier to add right now. 60 plus 30 is 90, plus another 90 is 180. Yeah. Thanks. They add up to 180 degrees, so I think I believe these results. Cool. So, let's also recognize one thing. You can draw similar triangles to compute any inverse trig function. Let's try to use inverse trig to compute, to think about something like inverse cosine of 2 over 3. Let's draw a picture of the angle inverse cosine of 2 over 3. Negative 2 over 3. So, first things first. Negative 2 over 3 is negative. So this angle, I'll be feeding it a negative input, will be between, it looks like between pi over 2 is the lowest it could be, and pi is the biggest it could be. So by looking at this graph, that graph, this is between pi over 2 and pi. Oh, neat. That's quadrant 2. So if you wanted to draw an angle of inverse cosine of negative 2 over 3, you could. It'll be an angle, so that when you draw that angle, the adjacent has side length 2, but pointing in the negative direction. And the hypotenuse has length 3. Adjacent over hypotenuse is negative 2 over 3. Cool. You'll need to do something similar when you think about inverse sine of negative 1 over 4. All right, so let's compute things that look like trig function of inverse trig function. So, some things like this work out exactly how you'd expect. And let's see that. So let's try to compute the cosine of the inverse cosine of 1/2. And let's start by thinking about inverse cosine of 1/2. So this is the angle with, oh no, I wanted to compute, we're not going to compute this by thinking hard. We're going to compute this by using that we know what these are. So let's start by computing inverse cosine of 1/2. Let's use the unit circle to do that. So how do you compute inverse cosine of 1/2? Well, you look for an angle between 0 and pi. So in this range, where cosine is 1/2, cosine is 1/2 there, that gives me a pi over 3. So cosine of inverse cosine of 1/2 is cosine of pi over 3, because inverse cosine of 1/2 is pi over 3. All right, let's go back to the unit circle and compute that. So now look at an angle of pi over 3. I want the cosine of pi over 3, so I want the x value. Oh, that's cool. Inverse sine of the sine of 1. Let's play the same game. Negative 1. So sine has a range negative pi over 2 to pi over 2. So I'm looking for an angle in this range where sine is negative 1. Right there. That corresponds to negative pi over 2. Oh, okay. What's the sign of negative pi over 2? Negative pi over 2. Negative 1. So it sure looks like the cosine of the inverse cosine of x is always x. The sine of the inverse sine of x is always x. With one thing you need to make sure to check. Let's try to think about the cosine of the inverse cosine of 12. And maybe I'll even encourage you to pull out your calculator, ask the calculator to compute this. It'll give you something interesting. So do it. I bet it gave you an error, right? If I ask the Google calculator what the cosine of the inverse cosine of 12 is, well, it just doesn't tell us anything. Which, no, I shouldn't just click around random links. Yeah, that's wrong. Yeah. Don't trust anything that you see online. Oh, here's maybe a good way to check. Let's pull up Desmos. You want to compute cosine of the inverse cosine of 12? Let's compute cosine of the inverse cosine. Oh, damn it. There's what the graph looks like. I want to plug in x equals 12. That just means I want to see where this red graph crosses x equals 12. And it doesn't. It doesn't. This doesn't exist. Why does it not exist? Well, think about what inverse cosine of 12 means. That's an angle whose cosine is 12. There is no angle with cosine equal to 12. Biggest cosine can be is 1. So this is asking you what is the cosine of something that does not exist? Well, you can't take that cosine. This whole thing just does not exist. So here's the resulting conclusion. Cosine of the inverse cosine of x is x. Sine of the inverse sine of x is x. Provided that x is a reasonable thing to plug into inverse cosine. It has to be between -1 and 1. Otherwise, the thing on the left side of those equal signs do not exist. Nice. All right. What if we go the other way? What if we try to compute the sine of the inverse sine of theta and the cosine of the inverse cosine of theta? And here, I've put a theta there for a particular reason. I put thetas there because I want to think of that as an angle. It's something I'm taking the sine of. You take sine of an angle. And well, if you graph it, you'll get one of these two graphs. Let's decide which one's which. Let's not do it by like thinking hard. Let's do it by actually having your computer graph these, and then we'll label them. So let's compute arc cosine of the cosine of x. There it is. There's the inverse cosine of the cosine of x. It starts at the origin. They both start at the origin, though, it looks like. It goes up until pi 0, up to this point at pi. Goes up to that point at pi. Yeah, this is the graph of cosine inverse of the cosine of x. Or here I'm using an x because I'm graphing the thing, so the x variable should be called, the data x coordinate should be called x. So this must be the graph of sine inverse of sine of x. Let's just see. Arc sine of the sine of x. So it looks like both of these have these nice like sawtooth pattern looking things. So, yeah, let's try to do this by like plugging in the number. So we, on the one hand, we know the answer, but we could also compute some things directly. So if I want to compute the cosine of, inverse cosine of the cosine of pi, well, I know the cosine of pi. Cosine of pi is -1. So cosine of pi is -1. Inverse cosine of pi. I want an angle that's between 0 and pi, which has cosine -1. Pi is the angle I want. If I want the sine of the inverse sine of pi, well, the inverse sine of the sine of pi, rather. Sine of pi is 0. Sine of pi is 0. Now, I want to look at the unit circle. I'm only allowed to use angles between -pi/2 and pi/2. I want to know where is sine equal to 0. Right there, I see the 0 on the whiteboard, so that's sine at an angle of 0. So, it looks like sine, inverse sine of the sine of x should go through the point pi 0. Inverse cosine of the cosine of x should go through the point pi. Pi 0. Cool. All right. So, the last things I want to do with this recorded lecture is I want to think about a thing I've been doing on the unit circle an awful lot. Let's think about a range of inverse sine and a range of inverse cosine on the unit circle. The range of inverse sine is -pi/2 to pi/2. There's an angle of pi/2 up to an angle of pi/2. So it looks like quadrant 4 or quadrant 1 is the range of inverse sine. Range of inverse cosine goes from 0 to pi. 0 to pi. That looks like quadrant 1 or quadrant 2. So I'm even going to flip back to this first page and write a thing in. The definition of inverse sine of 1 over 8 is the angle in quadrant 1 or quadrant 4, which has sine of theta equal to 1 over 8. And notice, if I wanted sine of theta to be 1 over 8, well, it can't be in quadrant 4. Sine is negative in quadrant 4. Cosine inverse of negative 1 over 8 means the angle in quadrant 1 or quadrant 2 with cosine equal to negative 1 over 8. Since this is negative, it can't be in quadrant 1. In quadrant 1, cosine is positive. This angle is in quadrant 2. Groovy. So, with that thing pointed out, let's close with the thing that I want to close with. Or am I? Very last. Excellent. Okay, good. Here's a how-to. Let's suppose I ask you to compute the inverse sine of the sine of absolutely any input. So, we'll go through these steps by reasoning through how to compute it, and then we'll check by looking at a graph. And I really want to emphasize the check by looking at a graph because this stuff can get dicey. It's worth knowing that your answer is right before you do something silly like turn in your homework. So, let's do that. Let's compute the inverse sine of the sine of 17 pi over 3. So, the code for a question like this is inverse sine of a number is supposed to be like the simplest angle whose sine is equal to the sine of that thing. So, what do I want? I want to find the simplest angle with the same sine as 17 pi over 3. So let's try to do that. Let's start by thinking about 17 pi over 3 and figuring out what that is. And maybe it's worth doing some division. 3 goes into 17 5 times with a remainder of 2 thoughts. So long division says 17 pi over 3 is the same as 5 pi plus 2, I'm going to write it this way, 2 pi over 3. We can draw a picture of that angle. All right, that's 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. And now I need to go an extra 2 pi over 3. So that'll get me all the way over to here. There's an angle of 17 pi over 3. All right. Let's throw out any excess 2 pi. Well, no, let's not actually do that. Let's jump right down to the next step. Let's think about properties of trig functions. We've drawn this. There it is. Let's realize it as a simpler angle. So what's the simplest angle you could possibly use to describe 17 pi over 3? So let's see. It was, to get to here was 5 pi. And then I took another 2 pi over 3. That was a pi over 3. There's another pi over 3. So I could get to the same place by going backwards by pi over 3. Hello.
Hi.
You're here quite early. Okay. You'll be listening to me talk to myself for just a little bit.
Okay.
Cool. The simpler angle we could realize that as is negative pi over 3. So now let's ask ourselves if this sits in the right quadrant to be in the range of inverse sine. It does, right? It's in quadrant 4. The range of inverse sine includes quadrant 4, so that's fine. Don't need to do that. So the angle that we have right now is negative pi over 3. Let's see if we're still happy. Let's add or subtract some 2 pi's if needed to get this angle to live between negative pi over 2 and pi over 2. Oh, negative pi over 3 is between those two things. Right? Dividing by something by 3 is less than dividing it by 2. So it's in that range. So the inverse sine of the sine of 17 pi over 3 is negative pi over 3. To check that, let's maybe even look at a graph. We can graph the inverse sine of the sine of x. There it is. I want to see what happens when x is equal to 17 times pi over 3. Let's see where they cross. About negative 1.047. I'm going to write that down because I have no memory. The graph said that's what it should be about. Negative pi over 3 is in fact about negative 1.047. I lost the negative sign. So, computer checks out. All right. So here's, I think, the last thing I want to do. Let's try to do the same for the inverse cosine of the cosine of 17 pi over 3. So, first couple of steps are the same. 17 pi over 3 by the same bit of division is 5 pi plus 2 pi over 3. If I'm going to write it that way, I shouldn't have that pi there, should I? So, I can realize this as a simpler angle in exactly the same way. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and then 2 more pi over 3's. There's an angle of 17 pi over 3. I could get to that same end point by instead rotating backwards by pi over 3. Does this angle sit in a quadrant, a correct quadrant to be in the range of inverse cosine? Well, let's see. It needs to be in quadrant 1 or quadrant 2. It's in quadrant 4. That's bad. If not, then I need to reflect it. I need to do a reflection that preserves cosine, so it preserves the x value, and lives in quadrant 1 or quadrant 4. Let's reflect over the x-axis. So that'll replace negative pi over 3 with plus pi over 3. Do I need to try to subtract some 2 pi's to get it to be between 0 and pi? Nope, it's already there. It won't always be, right, depending on what you use as a simple angle and how you reflect. So it looks like the final answer is that the cosine of the inverse cosine of 17 pi over 3 is just pi over 3. And again, let's check. Inverse cosine of the cosine of x. X I'm going to plug in to be 17 pi over 3. 1.047. Pi over 3 is about 1.047. The calculator checks out. All right, cool. So I'm going to flip back to this previous page to fill in just one blank that I didn't because it wasn't relevant that time. If your angle doesn't sit in the correct quadrant to be in the range of inverse sine, then you need to reflect over the y-axis. We didn't that time because it was already in the right quadrant. But sometimes you need to reflect over the y-axis, in which case you need to think about what the simpler angle will become when you reflect it over the y-axis. All right, wonderful. Well, it's now 17 minutes before class. So I guess I'll start seeing people in about 17 minutes, if not sooner. Ciao.